Okay, the derivative as a function. So we took a look at derivatives yesterday, but now we're going to take a look at them in terms of functions. And it is true that a function's derivative is calculatable. We say differentiable on some interval, ab, if the derivative exists on that same interval. There's a definition for you. Let's take a look at an example. If we start off with a function 2x squared minus 1 and try and calculate its derivative, we end up using the limit formula as h goes to 0 of f of x plus h minus f of x, all divided by h. I find it useful to actually write out what we have f of x here, but I find it useful to actually list out what f of x plus h is as well, so that I can just substitute it in. So in this case, it's 2x plus h squared minus 1, which is 2x squared plus 4xh plus 2h squared minus 1. Then I can take the limit as h goes to 0 of 2x squared plus 4xh plus 2h squared minus 1 minus f of x, which is 2x squared minus 1, all divided by h. So this is using the definition of a derivative, sorry. And so I get 2x squared, take away 2x squared, minus 1 minus minus 1, which is plus 1. I get 4xh plus 2h squared over h. And as we've seen in the past, h's cancel. And I have the limit as h goes to 0 of 4x plus 2h. Applying the limit gives me 4x. So the derivative of our function is always 4 times x. There are some equivalent notations for f prime of x equals 4x. We can also write this as the derivative with respect to x as 4x, or the derivative of our function with respect to x is 4x. All of these are equivalent notations. Let's take a look at some rules. The first rule is the power rule, and it states that when you take the derivative of, with respect to x, of x to any power, you get n, which was the power, times x to the n minus 1. So you drop the power by 1 and bring the exponent in front as the coefficient. Let's take a look and see how that works. If you have f of x is equal to x squared, with this power rule, I no longer need to use the definition of a derivative. I can simply apply the rule, the power comes down in front, and the 2 drops down a power to power of 1, which I don't need to write, so the derivative is 2x. That means the slope at any point of our graph is 2 times the x value. That's a lot faster than what we were doing in the past. And it works like that for essentially any. So x to the 6th is 6x to the 5th. Drop the exponent as the new coefficient. Drop the degree of x by 1. And it works for any variable. So if we happen to be doing the derivative with respect to t of t to the 5th, we get 5t to the 4th. There's some other rules as well. There are the sum and difference and constant multiple rule. The sum and difference rule says that if you have either the sum or the difference of some functions, and you take the derivative, you can find that by taking the derivative of the parts. So and the constant multiple rule, which states that if you have a constant times a function and you go and take the derivative, you can just take the derivative and multiply it by that constant. So let's take a look at a couple of these in examples. Firstly, if you have a function like a polynomial, that's a function with a constant in front of it, added or subtracted by another function, add or subtracted another function. To find the derivative, you can take the constant and then apply the derivative of x to the fifth, take the constant and apply the derivative of x, and take the constant and apply the derivative, and you get this piece here becomes 5x to the fourth times 2, which is 10x to the fourth, minus 3. This piece here becomes 1x to the 0, which is multiplied by the negative 3, and that gives you minus 3, and the derivative of x to the 0 becomes 0x to the minus 1, and 0 times anything is 0, so the derivative of the last term disappears, and I have a final answer of 10x to the fourth minus 3. Notice that the derivative with respect to x of x is always equal to 1. And the derivative with respect to x of cx will always be equal to c. And the derivative of a constant function, the derivative of just c with respect to x, will always be equal to 0. That'll save you a little bit of time. Here's another example. Find the tangent line equation to the function 5x cubed minus 2x squared plus 5 at x is equal to 1. So the first thing that we should do is go and calculate the derivative. So the 5 times 3x squared minus 2 times 2x to the 1, and then the constant function drops off, so that's 15x squared minus 4x, and the slope at 1 is 15 times 1 squared minus 4 times 1, or 15 minus 4, which is 11. And then I can use y minus f of a equals f prime of a times x minus a, the slope, point slope form, to get the slope of the line. The function evaluated at 1, f of 1, is 5 times 1 cubed minus 2 times 1 squared plus 5. So that's 5 minus 2, which is 3, plus 5 is 8. And the slope was 11, and the a value was 1. And solving for y, I get 11x minus 11 plus 8, or y equals 11x minus 3. There it is in slope-intercept form. You can verify this graphically by taking y1 as your original function, much like we did in the video yesterday, and y2 being the slope of the line, and seeing that this is the slope of the line at that tangent point when x is equal to 1. So try that out on your graphing calculator to verify this. Another derivative rule is the derivative of e to the x. If you ever take the derivative with respect to x of e to the x, the cool thing is you just get e to the x. If we see this in an example, it looks like, let's do f of x is equal to 5 e to the x plus 3x squared. So the derivative is a constant function times the derivative with respect to x of e to the x plus a constant function times the derivative with respect to x of x squared is 5 e to the x plus 3 times 2x to the power of 1, which is 5 e to the x plus 6x. Of course, sometimes functions aren't differentiable at certain values. Let's take a look at an example where that occurs. So in this example, we're given f of x is equal to x to the 1/2, and we're going to show that the derivative is not differentiable, which means it doesn't exist when x is equal to 0. So let's try and take the derivative. So the derivative with respect to x of x to the 1/2, this is a power rule question. I drop the exponent by 1, and that's the same as 1 over 2 to the x to the 1/2, or if you use root notation like this. So there's your general derivative, and we want to see what happens at x is equal to 0, and of course I substitute in a 0, which is 1 over 0, which is infinite, which is undefined, so f prime of 0 does not exist as an actual value. Enjoy the homework.